Find the electric field at a point midway between two charges of 6 millicoulombs and negative 2 millicoulombs separated by a distance of 22 centimeters. So first thing we're going to do is draw a picture. So we have a positive 6 millicoulombs. I'm going to call that Q6. And it is 6 millicoulombs, so that's 6 times 10 to the negative third coulombs. And then I also have a charge of negative 2 millicoulombs, so I'm going to call that Q2. And that's, again, times 10 to the negative third coulombs for millicoulombs. And then they are separated by a distance of 22 centimeters. So this entire distance is 22 centimeters. And I want to find the electric field at a point midway between the two. So right here is where I want to find the electric field. Okay? So when I'm looking at that, what I'm going to do is I'm going to find the electric field created by the 6 millicoulomb charge, completely ignoring the 2. And then I'm going to find the electric field created by the 2 millicoulomb charge, ignoring the 6. And then we're going to use vector addition to combine them. So the first thing I need to look at is, well, which equation am I going to use? Well, I know the electric field is equal to Coulomb's constant times the charge creating the field divided by the distance from the charge squared. So I need the distance from the charge, not the distance between the two charges. I'm finding the electric field here. That's halfway between them. So that means that the distance from Q6 to where I am is 11 centimeters, and we should convert that to meters, so 11 hundredths of a meter. And we'll use the same logic to figure out that this is also 11 hundredths of a meter. So let's go ahead and first find the electric field created by charge 6. So Coulomb's constant, 8.99 times 10 to the 9th, times the charge, which is 6 millicoulombs, so 6 times 10 to the negative third, divided by the distance in meters, so 11 hundredths of a meter squared. And I find the electric field created by the 6 millicoulomb charge is 4,457,851,240 newtons per coulomb. It's a very big magnitude there, but we still need to include a direction with that. So we know that electric field lines point away from positive charges. So the electric field line is going to be pointing to the right. So when I am standing here, the electric field line is still pointing to the right. Okay? So this is going to be, the direction is going to be to the right. Okay, next, let's find the electric field created by the 2 millicoulomb charge. So we have 8.99 for Coulomb's constant times 10 to the 9th. And then we've got the charge, which is 2 millicoulombs. It's negative 2, but we just use that for direction. So 2 times 10 to the negative third, divided by the distance in meters, so 11 hundredths of a meter squared. And we find that the magnitude for electric field 2 is 1,485,950,413 newtons per coulomb. And again, we need to figure out the direction. Well, electric field lines point towards negative charges. So if I'm standing here and I point towards the negative charge, I'm going to be going to the right. The last step is to combine these two by vector addition. Okay, so the net electric field is going to be equal to, and we're going to add these vectors together, and what's nice is they're both pointing to the right, so they're both positive. We don't have to worry about any angles or anything like that. So we've got 4,457,851,240 plus 1,485,950,413. We add those two together, our net electric field is going to be 943,801,653 newtons per coulomb. And that is still going to be directed to the right.